my project for this past, do we need the timer going? There we go. I shouldn't have said that. I could have my timer. So my project this past summer was designing a broadband Wilkinson divider for the Allen Telescope's Arrays radio frequency conversion box. And I worked with Alex Pollack. I'm a student from University of Illinois, Urbana-Champaign. We'll talk about what those words mean in a second. So the Allen Telescope Array, it's an interferometer of 42 dishes. They're 6 meters, and they have this signal path. Many people here are used to dealing with signals in their computer, but those signals need a way to get there. They don't just magically go from space into computer. There is a signal path that involves analog components digitizing this. And specifically, this signal path is kind of old. It has some limitations. Some of those limitations are in the RFCB. Previous interns worked on the PACs. There's new Antonio feeds, but to try to expand the bandwidth of this array, there can be upgrades to RFCB. And one component in the RFCBs, the radio frequency conversion box, that can possibly be upgraded is this power splitter. Alex, my mentor, suggested let's try making a Wilkinson divider for this. It's a pretty strange and kind of novel idea, because Wilkinson dividers are generally not broadband components. I'm not going to go through explaining everything here, but the thing that you need to understand is the length of this trace on the divider is related to the wavelength of light that you're getting in, and away from that wavelength, your operation falls off pretty drastically. There's some technology that we can mitigate that with, for example, a coplanar waveguide instead of a microstrip, which this uses. Possible that with a coplanar waveguide, we'll have be able to just have cleaner signals, and it'll be good enough for our specifications. And there's also the concept of a step divider, which we'll talk about in a second. Another thing to understand is scattering parameters. I don't want to throw this at you, but it's so important. These tell you how electrical signals propagate through networks. You have reflection at input and output ports. You have isolation, and you have transmission. Generally, you want the transmission to be close to 0 as possible. It says -3, but really close to 0. And then everything else should be as low as possible. The first step to trying to design a new RFCB and a new divider is getting a box to put this divider on. And this was greatly figured out by a previous intern, Monica Schaefer. She worked on the PACs, and she figured out how to make a coplanar waveguide for this specific substrate and such with optimized parameters. I took that, I took some manufacturer sizes, I took the size measurements of the RFCB box, and we made it. And on the left, you can see we have a coplanar waveguide just sitting in space. On the right, it's enclosed in an aluminum enclosure, and the S parameters look great. It's, as you can expect, they look a little bit worse in the aluminum, but it still works. So we tried a first attempt at the divider. I bit off a little more than I could chew here on the left, and I got complete spaghetti as my result. And I learned from that experience to start small. And I thought I was starting small, but I learned what small really was, which is just start with the simplest thing you can. This divider here, which gave us some things which we like to see, but we're not getting that broadband operation, and we're not getting a good reflection at the output ports. Well, the technology that we can do to get some broadband operation out of this is having a stepped divider. By using a multiple stage divider with multiple isolation resistors, you can take advantage of this thing called a Chebyshev transformer, and achieve a more broadband response from your divider. There were, within all the literature that I reviewed, there were 2 divider designs which could possibly work here. The bottom one uses their own resistors, custom made with length, width, and impedance. That's kind of hard to replicate. And the top one has a pretty simple design that uses a solid strip line, a suspended strip line, I'm sorry. And suspended strip line also involves changing the shape of the box, but it might be possible if we do a coplanar waveguide to get good enough response for our things, for what we want. So we tried another attempt, and we can see that we got a broadband response out of it. That's great. Unfortunately, reflection at the output ports is still too high. Alex suggested let's make them circles. This way we can put vias in between the traces. And well, it's a little bit nicer, I suppose. We're running into the same issues here. And really the divider on the left, when we bring it down to single stage, this graph looks very similar to our initial design with corners that is kind of ugly. We want some smooth traces. This S parameter plot here looks very similar to this one. So sort of in conclusion, what we have out of this internship is a very nice simulation of the coplanar waveguide and the RFCB, and a partially working simulation of the Wilkinson divider. There, I chased down for multiple weeks trying to minimize any source of error that I could think of, and this is sort of the best result that I got, which has a too high reflection on the output ports to be useful as a divider. After that, there's isolation and frequency range, which can be tweaked and optimized. I'm pretty confident that we can get those to work, but this output reflection has been a challenge. There's two possible directions to take this in the future. We can either try to continue making this divider, or we can try to make a resistive splitter, which does not suffer from a broadband, from this narrow band operation related to the length of the wavelength, right? We could also just use commercial components, which work very well for this. This is just an example of one commercial component has VSWR, which can be equated to S parameters and decibels. That is very low for reflection. It's great. So thank you for listening to my presentation. Are there any questions?
Thanks. Questions?
Yeah.
Your plots you made with the S parameters, that was done in simulation?
Yes. ANSYS HFSS, high frequency structure simulator.
And you get some reflection of the output. How would you model like what was attached to the output? Is there just a perfect termination or something?
There's a wave port that is 50 ohms impedance matched and connected to top, bottom grounds and strip in the middle. I know that there's no problem with these ports because it works for the coplanar waveguide. For just the strip going through, it's the same design and the ports work. So that is one of many sources of error that I've sort of seen that very likely not the issue.
We have time for one more quick question. Again, if folks online have questions, feel free to unmute yourself. Yeah.
What are the pros and cons of using the commercial component versus designing it in-house?
The commercial component costs money.
Okay.
And it would be maybe, I would say, $500 per polarization, and it varies a lot depending on how you want to do it. It can be 2,000, but I would say probably able to find a deal for 500 per polarization, 2 polarizations per antenna, 42 antennas, and that's $42,000 plus tax or whatever. That's the ballpark. And also it takes up space. It might, I haven't looked deeply enough into this, but it might warrant making a new box and manufacturing 42 times 2 polarization more boxes with amplification inside of the RFCB, which would be another thousands of dollars. That said, it's not one of the most expensive things on that array. These antennas are expensive, but it's good to try to push science first, right?
All right, let's move on. Our next talk is from Ben.